with some logistic regression stuff. So up until this point, analyses that we've run throughout this entire semester, the past this entire year, limited to analyses of, or limited to models is looking at one or more continuous outcomes in terms of our dependent variable. This generally isn't a problem. Most of the stuff that we think about in terms of psychology, think about it occurring on a continuum, some sort of dimensional scale. So our models that are looking at continuous outcomes typically do a pretty good job of accounting for most of the stuff that we're doing. But sometimes we get into behaviors, processes, constructs, things like that, that are better addressed through some categorical outcomes, right? And in this situation, if we're looking at some outcome that's like legitimately like a yes or a no situation, or some sort of nominal outcome, whether or not you fall in this group, that group, or another group. Standard regression models, some of the general linear model stuff that we've gone up to this point are not good at handling that, right? And so we've got these models probably will take care of like 90% of the things that you wanted to address, but there's going to be some stuff with categorical outcomes. Other limitation of the models that we've gone up to this point, the general linear model stuff, there's a lot of assumptions, right? There's a lot of things that have to happen so that we can have some confidence in the effects that we're getting are statistically reliable. If those assumptions start to break down, then all of a sudden we start to get worried about whether or not we've got good effects. And as our analyses start to get more and more complex, we layer in more and more assumptions, and sometimes violations of those assumptions start to become problematic in sort of analyzing our models, okay? And so this is where we start to layer in some logistic models. So logistic regression. With the logistic regression, we're looking at some discrete outcome, okay? We're trying to predict some categorical outcome based on some combination of categorical, continuous, independent variables, okay? Nice thing about our logistic models, considerably more flexible, okay? With our logistic models, we don't have any assumptions based on the distribution level of measurement of our predictors. So all the stuff that it's better if they're nicely distributed. If they are, that's cool, but they don't need to be, right? So we don't have to worry about running through it, going through and transforming variables, and at least outside of the model, right? So we're less concerned with the distribution of our predictors with our logistic models. We also are not assuming linearity between our predictors and our outcomes, right? So we don't have to worry about that. We're not worried about equality of variance, stuff like that. So all of this stuff we spend so much time doing and going through and screening and actual analyses. Angela, how much time do you spend sort of in research projects actually running your analyses versus kind of putting your data together and screening and all that? Like, that's the stuff that takes so much time. It's the stuff that I'm having to do with these sets. Screening is probably taking much longer than the actual analyses proper, but that's just what this looks like, unless you just want to charge in, and then who knows if the effects that you've identified are going to work out. What's nice with the logistic models, we're still going to go through and do some screening more to just kind of get a good sense of our data. We're not worried that weirdness in our predictors is going to go through and start screwing around with our outcomes. So we just have a set of models that are much more robust. And so if you're working with outcomes that are naturally categorical in nature, then you're kind of forced into doing this. But we can also have situations where maybe I have kids looking at, let's say, substance use, right? And the vast majority of people are zeros, and then everybody else is at sort of 1 or 2 and sort of things along those lines. That might be a situation. So assumptions of our basic regression models are all screwed up. Maybe what we do is we just dichotomize that and say, we're just looking at users and non-users and just call it good. And then transfer over to a logistic model. And now all of a sudden, I've got a much more robust thing. I don't have to worry about sort of weird types of distribution and things like that, okay? Questions that we would typically ask with a traditional logistic model about can our prediction of some categorical outcome exceed chance based on a linear combination of variables. Okay, can I do better than just guessing average values of some type of outcome based on information that I have in terms of predictors, right? So similar to our standard linear regression, same type of thing. We're looking at prediction. Not always concerned about prediction, similar to our standard linear models. Basically, the question is, with our overall model fit, if we have a statistically significant model, it's saying, do these predictors do a better job, or do these variables do a better job in combination of predicting some outcome above and beyond just basically guessing the mean of your categorical variable. Okay. We can also look at unique relation of individual predictors with categorical outcomes. A lot of the language that we're going to be using in the interpretations are going to be very similar to the stuff that we've gone through in terms of regression up to this point. So looking at sort of whether or not controlling for other things, we are just finding a unique association between our predictors and our categorical outcome. Looking at whether or not external variables influence the magnitude and direction of relations between specific IVs and outcomes. What are we talking about right here? It's a moderation, right? We can run moderation the same way in a logistic model, same way we would run moderation anywhere else. And looking at to what extent does our model reliably classify individuals. If I am trying to predict my outcome and I know sort of what groups people are in, how well does my model then predict what, if I'm going to, when he's trying to predict whether or not people are going to identify a defendant as guilty, not guilty, can we collect variables that go through and reasonably or reliably predict which the outcome is going to be. These are really, really handy. These are underused models. We don't use these enough, and we should. There's just a lot of capabilities. We should be using these more in situations where sort of to answer some of the questions that come up. Okay? So, are people who here has done any work with a logistic regression previously? Okay. Anybody else work with these models at all? Okay. A little bit tricky in terms of odds ratios and sort of going through and getting sort of your understanding of what's going on with that stuff. But once you kind of get the hang of those interpretations, these are the very, very nice models if you have data that fit into them. Okay. So first thing we're going to do, we're going to talk about odds and probabilities. Important distinction to tease apart when we're working with this stuff. So let's say here, I don't know, this is from data Narina donated at one point in time. We have, let's say, data looking at rates of execution based on black defendants and white defendants. So we've got execution, yes, execution, no is life in prison. Total for our black defendants, white defendants, rates of death sentence, life, total here, basic 2x2 table with this sample that we've gone through and collected. Okay, so if we're talking about a probability, remember the probability, calculating a probability sort of based on the number of outcomes, target outcomes, over the number of all possible outcomes here, right? Probabilities are bounded by 0 and 1. We can't have a probability can't be greater than 1. I can't have over 1 in terms of probability of something that happens. Either 0, it never happens. 1, outcome always happens. Those are the limits, right? So if we're looking at the probability of execution overall, probability of execution here is 0.08. Evelina, how did I calculate the probability of execution as being 0.08 based on this table?
66 divided by 825.
Yep, 66, 825, right? So it's a probability. Probability of execution, these are the total numbers of executions. These are the total number of cases. This divided by this gives you 0.08, right? Evelina, if I were to say probability of execution of black defendant is 0.12, how would I get that?
33 divided by 825.
Yep, what's that?
33 divided by, 284 divided by 825.
Okay, so one more time.
1 second. 33.
33.
Divided by 284.
There we go. 33 divided by 284. Here, we're just talking about a subset of our sample, right? So if I'm a black defendant, what's the probability of being executed, at least within the context of this sample? Okay. So probabilities, we know probabilities, we like probabilities, probabilities make sense to us. We're comfortable thinking about things in terms of probabilities. We know what a high probability is, we know what a low probability is, right? If I say the probability of snow tomorrow is 80%, you know what that means. If I say its probability is 10%, you know what that means. Probabilities are nice, they're intuitive, we like working with this, right? What starts to get a little bit more confusing when we start talking about odds. Odds are different. Odds, if we're talking about an odds ratio, we're looking at the ratio of an occurrence to a non-occurrence of some type of thing. So an odds is going to be occurrence over non-occurrence. Odds ratio is occurrence over non-occurrence for one group, occurrence over non-occurrence for another group. Okay, and what we know is that what makes odds useful, at least mathematically from a modeling standpoint, probabilities are bounded by 0 and 1. Odds are not. Odds are bounded by 0 to infinity, right? We can't have negative odds, but what we do is we have odds to go on continuously from 0. It never happens to infinity, sort of massive increases in odds, right? So if we're looking at, say, the probability of execution for a black defendant is 0.12, the odds of execution for a black defendant is 0.13. Someone tell me how I calculated that odds, the odds of execution for a black defendant?
33 over 251.
Was it? Exactly, perfect. 33 over 251. The occurrence over the non-occurrence. That's going to give me the odds of execution for the black defendant, and then Kate, odds of execution for the white defendant?
33 over 508.
33 over 508, right? So we've got the odds of execution versus non-execution for a black and white defendants. And then our odds ratio is going to be, our odds ratio for the execution of a black defendant relative to a white defendant, this is going to be 2.02. So Haley, how did we get the odds, how did we calculate that odds ratio?
You divided 0.13 by 0.06.
Exactly, right? So we've got the odds of execution for a black defendant over the odds of execution for a white defendant gives us an odds ratio. Now the odds ratio starts to get, people get tripped up on this, and it's kind of a difficult thing to kind of wrap your head around. But what we would talk about in terms of interpreting this, talk about the likelihood, and don't, when you're interpreting the odds ratios, don't use the word probability. Probability doesn't need to go in the interpretation of an odds ratio because it's not a probability. Talking about likelihood and things along those lines. But we would say if our odds ratio is, or if we're talking about the odds for our, just our odds for our black defendant. Odds for a black defendant is 0.13. So we could say the odds is 0.13. We could also say the likelihood of execution among black defendants is 0.13 times that of non-execution. So does that mean execution is likely or not likely? What do you think, Nick?
Very.
What's that?
Execution is very likely.
Very unlikely, right? So the odds of execution, think about multiplying things by, is that not what you said? Confirmation bias, I'm hearing what I want to hear.
I think I said likely, but I might have likely.
Okay, so basically what we're saying, right, if I've got an odds of 0.13, right, it's saying that sort of the odds of this happening versus this happening are a fraction of, so it's a fraction of sort of the other in terms of this, right? And so sometimes odds can be difficult to express in terms of a way that's intuitive. So what we could do is we could start in talking about this in percentages of likelihood. What we could do is we could say execution is 87% less likely than non-execution for black defendants, right? So we take our odds ratio, we subtract it from 1, and then so we would say if an odds is if I have an odds of 1, what does that mean? If I said, if here the likelihood of execution, if our odds of execution for black defendants versus non-execution was 1, what would that mean? If I have an odds of 1.
That the likelihood of execution, non-execution is the same?
Yeah, it's equal, right? I've got even odds, right? If I'm gambling, if I've got even odds, it means that sort of basically it's a coin toss, right? Equal likelihood of execution versus non-execution. So if my odds is less than 1, what does that mean? That my target outcome is less likely. If my odds exceed 1, it means target outcome is more likely, right? And so we can start to play around with this a little bit. Odds are difficult things to kind of think about, but if we could go through and start manipulating this, so I can say the likelihood of execution among black defendants is 0.13 times that of non-execution. That's an odds that's less than 1, suggests that the likelihood of execution is less than likelihood of non-execution. I can put that in more sort of meaningful terms, take my odds and subtract it from 1. And I say the likelihood of execution is, so execution is 87% less likely than non-execution for black defendants. That's something that's more intuitive, right? I'm like, okay, execution is still pretty rare, sort of given the whole thing, right? Or what I can do is I can flip this around, right? I could, instead of looking at the odds of execution, I could turn this in, report this in terms of non-execution, right? So then I just flip my, my categories around. I take 251 divided by 33. Now I'm reporting this in terms of the likelihood of non-execution versus execution. And in this situation, if I do that, what's 251 divided by 33?
7.6.
What is it?
7.6.
7.6, right? So I would say that the odds of non-execution for black defendants is 7.6 times that of execution, right? And so that kind of helps, that makes some sense too, right? So here we're just interpreting odds, but if we go through and start talking about odds ratios, we're talking about one odds versus another odds. And so here we might say, so we calculate the odds ratio of execution for a black defendant is 2.02, right? We would say here, and if it's equal odds, if the odds of being executed for a black defendant are equal to the odds of being executed for a white defendant, Layla, what would my odds ratio be?
I'm sorry.
Yeah, if the likelihood of execution for a black defendant was equal to the odds of execution for a white defendant, what would my odds ratio be? It's even money. It's even money. 1. There we go. It would be 1, right? And so when we're interpreting our odds ratios, what we need to do is we need to take that odds ratio. If 1 is our baseline, what we do is take our odds, subtract our 1 from our odds ratio. And so here, if we get 2.02, we subtract 1 from that, we get about 1. And so what we would say, the odds of execution are approximately 100% greater for black defendants as compared to white defendants, right? Or if we're just interpreting the odds ratio, likelihood of execution for a black defendant is approximately twice that observed for white defendants, right? And so this can be a tricky thing to go through and sort of wrap your head around, but do people kind of see how we're playing around with these odds ratios and making some interpretations here? And people don't, again, when people do these models, they don't interpret these well. There's a lot of intuitive, like really nice meaning. Now, some people get upset about odds ratios and say they can be misleading and talk about maybe risk ratios are a better way to communicate things. We won't get into that for sort of what we're doing here in this basic introduction. What I want you to do is just be comfortable in terms of if you're seeing an odds ratio or odds being presented, being able to interpret those, know what those mean, and then being able to interpret those in research that you might run across. Because this turns into a goddamn mess. When I'm reviewing papers, you like run a logistics and say the odds of this are greater than this, but all their odds ratios are less than 1. In fact, well, that's confusing. You're talking about it this way, but you actually run it this way. If you want to talk about it this way, you need to run your model that way so everything lines up. It's a confusing thing for people to get their hands on or get their head around, and so just wanting to be very clear when you're doing this stuff. Okay. The handout that I gave you, there's one that says, I don't know, he's working with a cohort several semesters ago, and so a massive email, and I thought, I guess maybe I'll just save that in terms of the text one. So just walking through the interpretation of odds ratios and sort of different ways we can go through and talk about them. Right, there's a lot of different ways you can express these depending on the data that you have. And so just wanting to be able to do this flexibly, talk about these in ways that make sense given the research question and so on and so forth. Angela, anything to add in terms of like just basic interpretation of odds ratios, working with odds ratios in the literature, things along those lines?
I think just like giving some different ways to talk about them. But yeah, just becoming familiar with how to interpret them in different ways that make the most sense given the question and given the direction that it's needed. Recognizing which one, which one makes the most sense, probably the majority.
Yeah.
Going at one and the other.
Yeah. And people will screw this up. People in published research will screw this up, and this is what this means. And you're looking at that, seems weird. If it seems weird, sit down, think about it, ask yourself literally what does this mean, because they may not be interpreting those odds correctly, and this starts to become important if this is the whole purpose of your study. Okay. So in general, even odds is 1. Sort of the odds of this group of an event occurring in this group is equal to the odds of an event occurring in that group. Even Steven, odds greater than 1 suggest that the target outcome is more likely in your target group relative to your reference group. Odds less than 1 means that the target outcome is less likely in your target group than your reference group. Okay. And we'll play around with these a little bit more in a moment. So thinking back and thinking about choosing a design that's as parsimonious as possible. If I just have this 2x2 contingency table here, we don't need to worry about a logistic model to test this. We just use a chi-square, right? A chi-square with these categorical analyses, sort of a good understanding of just basic chi-square categorical tests start to become important to help sort of get a better understanding of some of the stuff that's going on in here. So our chi-square test of independence, we're looking at the relation between the relation of dependence between the observed frequency of 2 nominal variables, right? Now in this case, we've got a 2x2 table. It doesn't have to be. I could have 2x3 or sort of however big your design wants to be there. But we're just looking at whether or not levels of this categorical variable appear to be related or dependent in some way on the level of these the other categorical variable. What we're doing with these models with a chi-square, what the statistic is looking at is comparing the observed frequencies to the expected frequencies, assuming the null hypothesis. Right? Null hypothesis says that x1 is unrelated to x2. Right? Our null hypothesis says that the race of our defendant has no relation with their sentence. Right? And so if that's the case, then based on our total number of samples we have in the breakdown of this, we can tell if there truly is nothing going on, if there is no dependency between these variables, there's a set of expected frequencies that we should see in these cells. And what our chi-square test is doing is it's comparing what we've observed to what we would expect, assuming that there's no relation between these two variables. So our chi-square statistic is just going to be calculated as the summation of our observed frequency minus our expected frequency, and that squared over the top of our expected frequency. Expected frequency, or here our observed frequency, is just how often a thing occurs, so just our cell count. Our expected frequency, we're going to calculate this as our column total times our row total over the total number of people we have in our sample, with degrees of freedom equal to the number of categories in our row minus 1, number of categories in our column minus 1. Okay, pretty simple, pretty straightforward to go through and do this. And so if I go through and calculate here my expected frequencies, these are the frequencies that I would expect for each one of these cells, assuming that nothing's going on. These variables are completely independent, right? So if I take, John, you got a calculator there. If I take my expected frequency for Black Death sentence, sort of based on here, right? If I take 66 and I multiply it by 284 and I divide it by 825, what do I get? 22.72. This is, if there were no relation between these two variables, this is the count or the frequency that I would expect for this cell, right? Same thing here, John, help me out here. For black non-execution, let's do this. Do white non-execution. If I take 759 multiplied by 541 divided by 825. Yeah, 497, right? So basically what is going on in the guts of your chi-square analyses is, and so in the history of our science, before the advent of computers and computing power and things like that, these were really nice analyses to run because they're fairly easy to calculate. And so you just go through and put this together. And so this is, you used to see a lot, if you look at research from the 50s and 60s, a lot more chi-square stuff, right? Because I don't have SPSS to just crank things out. Running a regression model or something like that is going to be really labor intensive. These are pretty easy to go through and do. So we see a lot of dichotomizing or median split type of things, just because the calculation is actually pretty easy and straightforward. So if I wanted to calculate my chi-square statistic for this 2x2 table, I would just take, I would go through, look at my observed versus my expected frequencies for this cell, right here, for this cell, down here, for this cell, here, for this cell, here, sum all those up, and this gives me my chi-square test, my statistic value, my value for my chi-square statistic here. I get a chi-square statistic of 7.74, chi-square based on my table with 1 degree of freedom, right? We've got 2 columns, or 2 rows, so 2 minus 1 is 1 times 2 columns, 2 minus 1 is 1, 1 times 1 is 1. I get a chi-square with 1 degree of freedom, critical value 3.84, that far exceeds it, right? And so we would say, based on this, we would reject the null hypothesis. This net sentencing and defendant races are sentencing and defendant race are independent, right? So this is nice. I mean, this is within a 2x2 table. If this is what we're looking at, we've just got 2 categorical variables. Wanting to see if there's dependency across these. Chi-square test is really nice, easy to calculate, pretty good. Right now it starts to get a little more tricky if you do see. If you get bigger chi-squares, if you do see a significant test, then you have to try and figure out exactly where some of that stuff is going on, right? But a really nice model for some of the stuff that we're doing. Okay. Questions on basic chi-square stuff? All right. So, chi-square models or chi-square tests are nice if we've got a couple of categorical variables, but sometimes what we want to do is we want to look at multiple predictors. We want to look at the interrelation of multiple variables, some continuous, maybe some categorical, on some type of categorical outcome. What we might want to know is, does the best linear combination of this set of predictors, how well does this do in terms of predicting levels of some type of outcome? Okay. Now the problem with this is that our probability function, right? What I'm interested in is the probability of someone being in group A versus group B. Problem is our probability functions aren't linear. Remember, our probability is bounded by 0 and 1. And what we see is as our probabilities start to get closer and closer to those limits, changing the expected value of y given a change in x starts to taper off. Right? In our linear models, if I'm asking about, if I'm interested in the relation between I'm looking at the relation between neuroticism and quality of life, right? This is continuous, this is continuous. I can go through and regress as neuroticism increases, quality of life decreases. I've got a line that just goes off into infinity. Like however much neuroticism and however low quality of life, so my model just projects things sort of in a straight line, right? Problem is with our probability, if I've got a dichotomous outcome, right? I'm trying to predict ADHD diagnoses, yes or no, right? Either people meet diagnoses, they're not. I've got a number of different predictors, and I want to know the probability based on these predictors, the probability that someone meets criteria for ADHD or not. Well, what happens is I start to get closer and closer. Like, so let's say, what's a thing that might predict diagnostic status for ADHD, John? Okay, so behavioral problems in class, right? What I would see is as behavioral problems increase, we're going to go and start to hit a point where I'm not getting much additional predictive value in the probability of ADHD. So if I go from sort of average levels of behavior problems in class to 2 units above, that's starting, the probability of ADHD increases quite a bit. But if I jump from 4 to 5, the increase in the probability changes. It starts to taper off. We get asymptotically close to 1, it sort of levels off, right? And if I'm here going from let's say the mean or the average level of behavior problems to 2 units below, you see a pretty significant decrease in the probability of having a diagnosis. As I start to get 3, 4, as that starts to become really, it starts to taper off, right? It doesn't tell me quite as much. And so what we've got when we're looking at probability, if probability is our outcome, which is technically what it is when we're working with these logistic models, right? What is the probability that someone falls into this group versus that group? What we're working with is a nonlinear function. As our predictors start to increase and increase, they don't just increase indefinitely in terms of the probability because it's bounded by 0 and 1. And so we get this kind of sinusoidal, this curved pattern where things kind of tape off. And if our outcome isn't follow a linear, if the relation between my predictors and my outcome isn't linear, I can't use a linear model because my linear model doesn't do a good job of accounting for this stuff, right? And so what we see is that the distribution of our the probability of being in one group versus the other, given a set of predictors, often follows this logistic distribution, okay? And this is going to be a logistic distribution here. And what we get is our probability, right? This is what we're looking at, the probability of being diagnosed with ADHD, right? What's the probability of being diagnosed with ADHD? Follows this function where we've got our linear model right here, our linear, basically our regression equation. We've got base E to our regression equation over the top of 1 plus base E to our regression equation, right? So we've got our standard linear function, the same linear model that we've been working with in all of our regression outputs and things along those lines. We've still got that. It's just not. It's just sort of in the taken to base E to the power of our linear model, right? And so the problem is that this does a nice job of accounting for what we're seeing. It just doesn't do a good job. It starts to get complicated because we can't just estimate this using our typical linear function. Okay. People understand sort of the conundrum we're in. So we were wanting to predict a probability. Probabilities aren't linear in their parameters. Probabilities are nonlinear. And so what we've got to do is we've got our general linear model, and we want to use this best linear combination of predictors to predict an outcome, but our outcome isn't linear, and that screws up our model. So what we do with our logistic regressions is we utilize a link function, okay? Basically what we do is we go through and we're transforming our outcome using some sort of transform. Talk about this transform as our link function. And the most common link function is going to be a logit or a log odds. Okay, so this is what we're wanting to predict. We're wanting to predict probability is going to be, the probability of our outcome is going to be equal to base E to our linear, to the power of our linear function over 1 plus E, and that's supposed to be a superscript there. 1 over, basically this thing is the same thing as that down here, right? So the probability that we would like to estimate is base E to the power of our linear function over the top of 1 plus base E to the power of our linear function. That's not linear though, But what we can do is we go through and transform both sides of this equation. What we find is a natural log function serves quite well as our link function. So if we take, go through and sort of run through our transform, what we end up with is the natural log of our odds here is going to be equal to our linear function, okay? And so what ends up happening is we've got a linear, with our logistic regression, we've got a linear regression that predicts the natural log of the probability of being one group over the probability of being another group, okay? And so what we're doing, remember here, oops, is we want to predict probability. That would be nice. We can't predict probability because probability is nonlinear in its parameters. But what we can do is we can go through and restructure this equation so that we can use a linear model to predict an outcome. It's just no longer the outcome that we initially wanted to predict. Our outcome is no longer probability. Our outcome is now the natural log of our odds ratio here, right? And so what we find is this logit, right? This log odds that we're getting, our logit here can be estimated using our linear function. We can predict a logit using our linear models. Our logit is bounded by 0 to infinity. Our logit can be used to determine the odds of being in a particular category versus another based on a set of predictors. So it's basically, we're still running a linear regression. It's just the linear regression. We're not in a linear regression. What we're doing, our regression model is giving us an expected value of our outcome. In this case, it's going to be the expected value of our log odds, right? Now, log odds probably don't mean a whole lot to you. They don't mean a whole lot to anybody. What we can then do is take those log odds to go through and start sort of moving things around and getting things that start to make some interpretive sense. Okay. Who's confused by this? Confused. Okay. So think about this. I like regression models. Okay. I want to use regression models. Regression models are nice when I'm trying to predict a continuous outcome. And that works out well. I can do that all day long. But sometimes I'm wanting to predict something that's not continuous. Sometimes I want to predict something that's categorical. And what I want to know is the probability of being in one group versus another group. Unfortunately, the probability of one group versus another group isn't a linear function, right? But what I can do is I can still use my linear model, my regression model, to predict not the probability of something that's going to happen versus not happen, but the log odds of something that's going to happen versus not happen, right? So it's not all that different than I've got a outcome variable that's has a horrible distribution, right? So I go through and I transform that, and that takes that thing that I wanted to predict, and the transform of that variable is now sort of has a better distribution, right? Logistic regression isn't all that different. I want to predict this thing, but it's kind of a crappy thing. It doesn't work with my regression model. But what I can do is I can transform that thing, and now all of a sudden, I'm predicting the transformed version of this thing, just like with a regular regression. If I'm sort of looking at predicting regression has a terrible distribution, so now I'm predicting the inverse square root of regression. I'm still not predicting regression. It's something different. But what I can do is then sort of back translate to go through and get it into something that makes some sense to me. That's functionally what's going on with our logistic models. This link function just takes this probability function, turns it into a log odds, and then what we can do is we can then use standard principles or our GLM to predict the log odds. Log odds is exactly what we want to get, but with some transformation we can back translate that into something that makes some sense. Okay. All right. So another thing that gets a little bit tricky in terms of our logistic models is we're not using ordinary least squares regression to model these. We're using a different estimator using maximum likelihood. Okay, maximum likelihood is going to be different than our OLS methods. Maximum likelihood is going to be a different approach where we're going through talk about maximum likelihood as an iterative approach where we're going through and basically in a more sophisticated way, we start with some starting values, right? So I want to get I want to estimate my coefficients for this model. What maximum likelihood is going to do in an iterative procedure, we're going to start with some starting values, and then we run a model with those values, compare it with the actual values that we observed, and see how good it is. First iteration, are we very good? Not so good, right? But based on that discrepancy, then we go through and we sort of tweak the coefficients. We adjust them a little bit, and then we run the model again, and maybe we're a little bit closer. And then we do this process over and over and over and over again until we start to see very, very small changes in sort of, basically our tweaking starts to produce less and less of an improvement. When we get to a point where changes in our model are sort of making very, very minimal improvements in sort of our outcomes, we would say that our model is converged. We've said once our sort of iterations are producing sort of this level of change in our model, then we're going to call it good, and we're going to say these are our estimates for our coefficients, right? So the goal of our maximum likelihood estimation, remember our goal of our ordinary least squares estimation is to minimize the sum of the squared residuals, right? We're just trying to get those squared residuals to be the sum of the squared residuals to be at the minimum point. Goal of our maximum likelihood estimation, what we're trying to do is we're trying to estimate parameters that maximize the probability of obtaining the scores that we are actually saying. So it's just a different estimation function. Maximum likely has some benefits. It's nice. You could assess a regression model with maximum likelihood estimation if you wanted to. This would just be doing a path model, and SCM is just you're going to be doing the same thing. You're probably going to get very similar, if you've got a good model, probably get similar coefficients for OLS versus maximum likelihood if we're just doing a standard regression. But if we're working on our logistic models, minimizing the residuals doesn't make any sense anymore, and so we're working with maximum likelihood format here. So just an example, right? So let's say I have this equation here. So I've got x2 plus y1 equals 9, right? Emilio, what's the best value of x?
You want me to use the table?
What's that?
You want me to use the table?
Oh, no, just based on this, what's the best value of x?
4.
What's that?
I would say probably 4. So y would be 1.
I'm sorry, what's
The
that?
best value of x for that equation?
Yeah.
I'll probably just say
4?
4. 1, yeah.
4, okay. 4 and 1, okay. What would be a different value?
3.
Yeah, so this could be 3, and then what would y be? 3. And what would be a different value?
2.
Right? Basically, is there a unique solution for this equation right here? No, right? My outcome here, I can go through and I can choose any of these is going to fit nicely in any one of these, right? Like there's not a unique solution for this equation. x2 plus y1 equals 9, I can't solve that, or I can just give you any number, and if I give you whatever number for this, then so I've got the number for that, right? And so I can choose anything that I would want, right? But if I go through and now I've got another equation here, now all of a sudden is there any value for x and y that I can plug into, or excuse me, can I just plug any value in for x and y that's equally acceptable for both these equations? No, right? I can't just go through and throw in whatever I want. Now I can go through, in this set of equations, I can solve this, right, into something that actually makes both of these equations true, right? If I go through and I say, x2 plus y1 equals 9, and x3 minus minus y1 equals 16, right? Basic algebra, I get x5 equals 25, right? So x equals 5, and if x equals 5, what is y? What's that?
I said 1. That was wrong.
1. What is y? You're close. If x is 5, what's y? What is it, Nick?
-1.
-1. Okay. This is a unique solution for this set of equations, right? 5 times 2 is 10, plus 1 times -1 is -1, gives me 9. 3 times 5 is 15, minus -1 times -1 is 1, gives me 16. So I've got a unique set of I've got a unique solution for this set, right? But so this is convenient. I don't need maximum likelihood estimation to go through and do this. But if these equations, and think about these equations as kind of like the data that you have, right? Basically what we're trying to find, and x and y are going to be coefficients in your model. What are the coefficients that best reproduce the actual data that we've observed, right? And what maximum likelihood is doing is it's going through and it's starting with some values, and then we tweak x a little bit, we tweak y a little bit, getting a little bit closer, we tweak x a little bit, get y a little bit, get a little bit closer, and start iteratively getting closer and closer to a solution until we get a point where sort of futzing around with our coefficients sort of making minimal changes in our model, and then we said that it's converged, and those are the coefficients that we'll go through. Okay, we'll get it. And maximum, it's sort of complicated mathematically and things along those, but just kind of conceptually want you to have a general understanding of kind of what's going on with this model. We're kind of getting the hang of this. Okay. So to this point, we've been talking about just our logistic models generally, but if we go through and we're just looking at an outcome that's dichotomous, takes on values of 0 and 1. What we're looking at is a binary logistic model. We can have multinomial logistic regression. I gave you a handout that says binary logistic regression, but it's not, it's multinomial. It's the one with more pages. On that, cross out binary logistic regression and write it. It'll say, yeah, it says binary logistic regression, but then exercise multinomial logistic. Cross out binary, right, multinomial. These multinomial models is when we're looking at categorical variables that have more than 2 outcomes. So I've got a nominal variable that has 3 separate conditions or something along those lines. We're working in a multinomial framework. We were not going to have time to go through multinomial logistics in class, but this handout kind of provides you an annotated sort of walking through one of these analyses in SPSS to try and give you a sense for what that might look like. But the models that we're going to focus on are going to be our binary logistic models. Binary logistic models are outcome dichotomous, going to take on values of 0 and 1. And what we're trying to do here is trying to predict the odds of falling into some criterion category relative to a reference category based on the best linear combination of our variables, right? So what we need to do, and it starts to become very, very important, is starting to think about, before we set these models up, what's our criterion and what's our reference group, okay? This starts to become important both for our outcome and for any categorical variables that we include as predictors, okay? If you just leave it a chance, maybe you coded your data right and it will turn out okay, but it starts to become crucial to getting a correct interpretation of your outcome, knowing what your criterion group is versus what your reference group is. So, let's say we've got some hypothetical data here, and what we're trying to do is assess the probability of falling based on, as I'm skiing, based on a function of trail difficulty and season. Okay, so in this situation, fall is my outcome. Fall is my criterion variable. So if I fall, it's a 1. If I don't fall, it's a 0. Right? So not falling is my reference group. Falling is my criterion. So basically, what I'm trying to do, I need to have my outcome variable coded So that whatever 1 is, that's the thing that I'm trying to predict. So one, we think carefully about what am I trying to predict, the presence or absence of this, and then sort of going through and making my determination there. Okay. So in this set of data, my predictors are difficulty, and we're going to pretend this is continuous. Okay. It's 1, 2, 3. 1 is least difficult, 3 is most difficult. This isn't a continuous variable, but for the purpose of this example, let's pretend that it is, right? And then my other predictor here is a categorical variable. This is another nice thing about logistic models is that they handle categorical variables within SPSS much easier than our regression models do. I mean, we can still look at categorical predictors in our regression models. We just have to code them on our own, things along those lines. Logistic will handle this for us. And so we've got a continuous predictor, difficulty, trail difficulty, and then we have season, autumn, winter, and spring. In this case, I've asterisked spring. Spring is going to be our reference group, okay? So again, needing to know for my categorical variables, what's counting as the reference group, or my outcome, what's counting as the reference group, and make sure that we're very clear before we can start to interpret our coefficients. So here's our data. Here's our sample of 15 people, whether they fell or not, difficulty of the trail, and what season the skiing was going on. Okay. And so our model, what we've gone through and we've done, we're estimating our outcome is a logit. Our outcome is a log odds, right? We're estimating the log odds of falling versus not falling based on trail difficulty and season. Okay. Now you'll see we have season 1, season 2. Why do we have 2 predictors for season in our model here? What do you think, Laura?
I think because those are the 2 of interest on the printer.
Yep. Screens of reference. So this is just going to be like in our last assignment where we're looking at belief profile, right? Our logistic models will handle our categorical predictors. They just need to be coded correctly. And so basically you're breaking it into a couple of dummies here, right? So we've got difficulty, season 1, which is autumn versus everything else. Season 2 is winter versus everything else. But basically, because we've got 2 dummies, if this is 0 and this is 0, who are we talking about? Spring, right? And so spring is going to be our reference group. So this is telling me, so the increase in the log odds, or the difference in log odds for autumn versus spring. This is the decrease in the log odds for winter versus spring. And here's the continuous trail difficulty for those. Okay. So what I've gone through and I've done is my regression equation, and my outcome is predicting log odds. But log odds isn't necessarily terribly intuitive or sort of meaningful, right? And so a couple of different things. We can go through and we can convert the log odds to the odds of one thing happening versus the other, or changing the odds of one thing happening versus the other. Or we can actually go through and exponentiate this out and actually calculate the probability of falling based on certain values in our model, right? And what we're doing here is we're going through, and if we take, here's my linear model, right? And here's my linear model right here. If I said, let's say, I want to know the probability of falling on a trail, assuming that it's winter and I'm on a trail 3, I can go through and plug this in and actually get out through exponentiation the probability, estimated probability of me falling based on this information. But what I need to do is I need to take the value of that linear function, and I need to take base e to the power, or sort of whatever that number is, take that over the top of 1 plus base e to this power, and this is going to give me an actual probability. SPSS isn't going to give this to you, but you can actually go back through and exponentiate and give, just like I could in a regression model, tell you the expected value of an outcome given sort of these values for the predictors. I can get a probability based on the coefficients that I get in my model. I can tell you the probability of something happening based on sort of the level, the values of my predictors. I just need to exponentiate that using this function right here. So basically, I get my expected value for my outcome, and then I take base e to that power over the top of 1 plus base e to that power, that gives me an actual probability function there. People see how we're manipulating sort of this stuff around to get stuff that might be useful. Okay. All right. Thinking about model fit. How do we go through and see whether or not we've got a statistically significant model? When we start getting into categorical outcomes, if anybody's interested in taking additional stat courses, quant courses as electives through the university, our additional stuff here is limited, but through the statistics department, categorical data analysis is going to be a really, really excellent class to take. What you'll look with this is you start looking at log likelihoods of different categorical outcomes and trying to use this as a measure of model fit. So for our logistic regression model, we're going to get a model log likelihood that's going to be basically calculated as your log likelihood value is going to be the sum of your outcome times the natural log of your expected outcome plus 1 minus your outcome times the natural log of 1 minus your predicted outcome. This is what that table would look like, okay? Just again, wanting you to get a sense for how things are made, right? Let's see, sort of my outcome in this case, for case 1, I fell, right? Based on my model, my predicted value of my outcome is 0.899. 1 minus my predicted outcome, 0.101. Y times the natural log of my expected outcome is going to be this value. 1 minus y, or 0, right? Times this is going to be 0. Going to give me a log likelihood value of negative 1.06, right? And so we can go through and we do this for each one of our outcomes. And what we do is we go through and sum these up, and this is going to be my log likelihood value for this model. And what we find is this log likelihood value, if we multiply it by -2, this log likelihood value falls on a chi-squared distribution with lower values of your negative log likelihood indicating better model fit, right? So the better I am at predicting whether or not I'm going to fall versus not fall, the lower my -2 log likelihood value is going to be, right? So if I've got 2 models, right, and these are nested models, in the one model I've got 3 predictors, and the other model I've got 2 predictors, right? I'm going to get a -2 log likelihood value for my full model with all 3 predictors, and then I can estimate another model with just the 2 predictors, and I can get a negative log likelihood for that. And what I can do is I can test whether or not which one of these models is a better fit. Does the addition of this additional predictor or set of predictors produce a reliable improvement in my overall model? And I can do this by going through and testing the difference in my -2 log likelihood values. So what I can do is I can have, if I have a base model and then a restricted model with only a subset of those predictors, what I can do is I can take the -2 log likelihood values of those 2, and it's going to go through and give me a chi-squared statistic where I can actually test whether or not sort of this model is doing a better job of predicting my outcome than the other one, right? And this starts to get into SEM models and things along those lines. As you start to get into sort of more complex analyses, these log likelihood values start to become important. So just want you to know what they are, kind of how they're being calculated, and what they mean. Okay. Now, -2 log likelihood in and of itself has 0 meaning, right? It's sort of like a covariance or something along those lines. Like it has no intrinsic value in sort of what's big or what's small. We're just using this as a comparison to determine sort of relative fit of model improvement, things like that. All right. Okay, cool. So we can go through and look at statistical fit of our models, and this is important, I would say. And think about this in terms of our R-squared for our regression models, right? What does the F-test for our regression model tell us, John? What's that? No, just for like a linear regression model. What does our R-squared value tell us? or our test of our overall model test tell us for just a linear regression?
There's like a non-zero.
Exactly. Our model just tells us whether or not our R-squared value is reliably different from 0. Okay, right? I can, with a large enough sample, maybe my model accounts for 5% of the variability of my outcome. Right? It's not 0. It's probably not a great model. Right? Same thing with our logistic models. The inclusion of our predictors might do a better job than just predicting by chance, right? But it doesn't necessarily speak to the practical utility of our model. And if we're doing this, what we want to go through and we want to now start to think about sort of how useful is our model practically, we can start looking at classification tables, okay? So for this outcome, basically, here's what I've actually observed. Did I fall? No. Or was there a fall? No. Was there a fall? Yes. And this is what my model ultimately predicted for a given individual. Did they fall? No or yes. Okay. So here we have true negatives, right? These are people who didn't fall, who our model said, yep, they don't fall. Here we've got our true positives. These are people who did fall, and the model predicted that they fell, right? In this off diagonal, these are our errors, right? Here we have a false negative. Person fell, but our model predicted that they didn't fall, so we've got a false negative right here. Up in this corner, we've got a false positive. This person didn't fall, the model predicted that they did fall, right? And so we were incorrect here. So overall, we got 66% of the people who didn't fall correct, 89% of the people who did fall correct, overall percentage correct, 80% here, based on our model, right? So I might go through and say, just eyeball that and say, hey, we did okay, right? Our model is okay in terms of predicting who fell and who didn't. Well, what we can start doing, and for clinical people, this starts to become increasingly important in terms of thinking about diagnostic outcomes and things along those lines. Did we get something or did we not? Starting to look at sort of different ways of going about this. So I can calculate based on this model sensitivity, okay? This is sensitivity defined as the ability of my model to correctly identify whatever my criteria was, okay? And I'm going to take this, calculate my sensitivity as my true positive, right? Which is going to be here, is in this cell, that's my true positive. That person fell and I predicted they were going to fall. Falling is my criterion, not falling is my reference, right? So I'm taking my true positive over my true positive plus my false negative, right? My false negative was this person that my false negative. My false negative I said didn't, I said didn't fall, but they did fall, right? So I'm going to take here 8 over my true positive, 8 plus 1, my false negative 1. That's going to give me my sensitivity value, okay? Specificity is my ability of my model to correctly identify non-criteria, right? How good am I correctly identifying non-criteria? My positive predicted value, this is flipping things around a little bit. So I'm looking at the percentage of cases identified as criterion by the model that actually were criterion. Oh, these are popping up. Let me just go through. I need to, my animation got all screwed up here. Okay, but anyway, going back to the beginning, sensitivity, right? This is what percentage of criterion identified, what percentage of my criterion were identified by the test, right? So of the total, let's say I got a sample and 20 people in my sample of 100 were criterion, right? How well did my model do in terms of identifying those, right? So what's the best way to identify? What's the best way to max out my sensitivity? So if sensitivity is telling me what percentage of the criterion were captured by identified by the test, how do I get a maximally sensitive test? I want to identify school shooters, and so here's my test of whether or not someone's going to be a school shooter. How do I maximally max out my identifying sort of shooters in that with that criterion?
Minimize the false negatives.
Okay. But more straightforward, what can I do?
Increase true positives.
Yeah, you increase my true positives. What else should I increase? My false positives. If I've got a test that just identifies everybody as a school shooter, my sensitivity is 1. I've caught all of them, right? What's the downside? My specificity is going to be garbage, right? It's because what I've done is I've over-identified people. Let's say I want to identify sort of binge drinkers, right? If I want a maximum sensitive test, I just identify everybody as a binge drinker, and then I've caught everybody, right? The problem is my specificity is going to be terrible, because specificity is what percentage of the non-criterion were identified as non-criterion, right? And so we start to get a balance here. Same thing, positive predictive value, sort of looking at this a little bit differently. Positive predictive value, looking at the percentage of cases identified by criterion by the model that actually were criterion. Positive predictive value, I would argue, is probably, in generally, what we're probably more interested in, right? Of the people who identified as a case, how many of them actually were, right? And then the same thing with negative predictive value, of the cases identified as non-case, of the individuals identified as non-cases, how many actually were non-cases, right? And so if we go through and we calculate sensitivity, specificity, it looks like we actually did pretty good with this, right? Our numbers are saying my sensitivity is 0.89. Functionally what this is saying is that of the people who fell, our test, we correctly predicted 89% of those people, okay? Specificity is a little bit lower, right? Of the people who didn't fall, how many of those correctly were captured or were predicted as non-fallers? Well, about 2/3 of those, right? Of the people who were identified as falling, how many of those actually fell? About 80%. Of the people who didn't fall, how many were, of the people who I identified as not falling, how many actually didn't fall? That's my negative predictive value right there, right? And so what we're doing with this is different ways of going through and thinking about how we fit this stuff together to give some sort of practical interpretation to sort of my model. This can get easy to sort of turn your head around and kind of be difficult to sort of think about. If you go through and take a look, make sure you see if you can calculate and replicate this stuff up here. You don't have this slide, I just popped it in like 5 minutes before I came up here. I'll go through and shoot it to you. But thinking about different ways to think about sensitivity, specificity, positive and negative predictive power, you know, thinking about sensitivity, ability of our test to correctly identify criterion, right? Of those in the criterion, how many did we get? Probability that the test result will be positive when the test is, when the disease or criterion is present. Probability of a positive test given a true case. So these are all different ways to think about and ask these sensitivity questions and some of these. So I'll go through, send this out to you so you can go through, take a look. I'll send you a paper that we put out in Psych assessment where I was looking at, the big question was of sort of our trauma screener, right? So if someone goes through and sort of indicates that they've experienced some sort of trauma on a checklist, what's the likelihood if when we actually come in and do a proper assessment with that person actually meets criteria? This starts to become a big question in my field because a lot of our trauma assessments is based on you indicating, so yep, this thing happened to me. But if we actually get down and actually talk to you about what actually occurred, oftentimes what you reported is not a criterion event, right? I check physical assault. And so then I say, okay, physical assault. Then I come in and talk with you, like, physical assault, what did you mean here? Like, I was in 7th grade and I got in a shoving match with a kid in the locker room. Like, okay, well, that's probably not a criterion event, right? Or, you know, like, oh, natural disaster. Well, I saw Hurricane Katrina on TV. Like, well, that's not a criterion event, right? And so looking at, within the context of sort of this, like, how for our checklist, how sensitive, how specific, positive predictive value, negative predictive value. Sort of tried really hard to do some of the stuff I teach you guys in class and sort of interpretation and stuff like that. I'll send that to you. You can read it if you want or not. It doesn't matter. But just as a sort of a way that I've tried to apply this into something that is important in my field, sort of think about some of this stuff. Okay. Have people run into sensitivity, specificity issues before? It starts to become relevant, and you get into diagnostic tests and things along those lines. Clinical folks, you'll talk with Tara about this stuff in assessment in the fall. So just kind of a good thing to have a general sense for. Okay. Questions? Okay. In our models, sort of looking through our SPSS output, a number of different ways that we can test the statistical significance of different individual predictors. Okay. If we're working with our regular old logistic models, or excuse me, our regular old linear regression models, we just look at the coefficient, we look at whether or not it's statistically significant, and if it is, it is. If it's not, it's not. We just call it good, right? Logistic models get a little bit tricky. What you'll find is there's a number of different ways to test the reliability of individual predictors. Some of them are better than others. Your Wald statistic, this is in any logistic regression table, your significant values is going to be based on this Wald statistic. Your Wald statistic is basically taking your coefficient, scoring your coefficient, dividing by the standard error of that coefficient, and testing that on a chi-square with 1 degree of freedom test. Okay. Problem is the calculation of that Wald standard error is inefficient, and the distribution doesn't exactly follow a chi-square with 1 degree of freedom. Okay, we've run into this lots of times before with Sobel, violations of assumptions. What we've got is a statistic that doesn't exactly follow the distribution that we're testing it against. And so what we see with simulation research is that this Wald test associated with elevated type 2 error. What does that mean, Kate, if I have elevated type 2 error?
You said it was significant, but it wasn't?
What's that?
Is that the one, or you said it was significant, but it wasn't?
Obviously.
So it was significant, you didn't?
It wasn't, right? I've made a type 2 error. It is a reliable effect, but I have not, I'm over-rejecting things, right? And so what we see with these Wald statistics tend to be unreliable, particularly if you're working with marginal significance values, right? If it's clearly statistically reliable, you don't have to worry about it. But the concern with the Wald test is you're going to reject more often than you should be doing, right? Now, despite sort of this known bias and known problems with this test, this continues to be the standard sort of way to go through and test things within these models. But luckily what we have is a different alternative, particularly for those predictors that have sort of marginal tests. What we can do is we can go through and physically and manually calculate the difference in our negative log likelihood value for models with and without the predictor. Okay. And remember, our negative 2 log likelihood, or our log likelihood values, give us an overall measure of model fit, right? And so think about this as being similar to if I were to calculate a regression model in a hierarchical model with the full model, and then I added a new predictor, and see if that changes as results in a significant R-squared change. Then I would say, yep, this predictor has a unique effect in that it increased my R-squared value with the inclusion of this. That's basically what we're doing. We're just using negative 2 log likelihood values for this. And this provides a much more precise, this is your gold standard for testing the statistical significance of individual predictors. So what we would do in this situation is we would go through and calculate negative log likelihood of the full model that has the predictor of interest, and then test that model fit against a negative 2 log likelihood value of a model that doesn't include that predictor, right? And so the model without the predictor in it of interest is a nested model, right? And then what we do is we compare, take the difference of the negative 2 log likelihood from the full model, from the restricted model, test that against a chi-square distribution with 1 degree of freedom, and that would tell us if we see that chi-square statistic, that chi-square change statistic is statistically significant, then it tells us, yes, that individual predictor provides a unique contribution overall fit of that model. Okay? This is our preferred value method for evaluating unique contribution. Oftentimes you won't see this just because statistical programs don't provide it. walled statistics provided sort of a general rough estimate of kind of what's going on, and if you've got things that are clearly sort of not on the margins, this is probably good enough, but this is technically the most precise way to go through and test the contribution of individual predictors. Okay. Another option is a Lagrange multiplier or score test. This is just an alternative way of testing models. If we exclude or include a predictor, Lagrange multiplier is kind of intermediate to sort of these two things. There's really no reason to look at this. I mean, if you're concerned that your wall is over-rejected, the unique contribution of a predictor, then you probably just go to just run this. This is kind of an intermediary. You'll see it, but sort of these are the two that are probably the ones that are going to be the most useful. All right, let's take a break. We'll come back, talk about interpretation of coefficients, and then jump into SPSS stuff. The last sprint. We're getting close. Okay.
Saving the rest of it.
All right. Want to go through, so we talk about how we go through and interpret sort of actual output from our models. So again, remember that our model, the linear model that we're estimating with this logistic regression, isn't actual probability. Our outcome, what we're actually predicting is our log odds, right? And so our coefficients represent change in the natural log of the odds ratio per unit increase or unit change in our predictors, okay? So our individual coefficients, unlike our linear regressions where our coefficients represent expected change in y given a unit change in x, our coefficients in our logistic models are expected change in the log odds given a unit change in our predictors, okay? So the problem is our log odds is what we had to create in order to run a linear model with this. The problem is that log odds in and of themselves aren't terribly informative. And so what we can do then is we can go through and take the coefficients that we get from SPSS and we can go through and exponentiate those. And this is actually sort of not a terribly difficult thing to do. All we need to do is we need to take whatever our coefficient is, so we take base e to that power, and then that gives us our odds ratio. So in our skiing example, our coefficient for trail difficulty was 1.01. We take 1.01 and take base e to the power of 1.01, gives us 0.275. This is our odds ratio, okay? And our odds ratio, remember, is going to tell us the odds of increasing the odds of falling versus not falling, giving a unit increase in trail difficulty. So holding all the predictors constant at 0, the odds of falling versus the odds of not falling, right, are multiplied by 2.75 for every unit increase in slope difficulty. So every time we increase slope difficulty, we're multiplying our odds by 2.75, okay? Now this starts to become important because this multiplied thing starts to increase sort of, or it's different than how we would interpret our x's, right? So let's say I've got, if in a standard linear regression, right, I have a coefficient for my predictor is 1.0, okay? So let's tell me what that, how, for a standard linear regression model, so my coefficient for x, or my coefficient for x is 1. What does that tell me? Okay, so remember, like, so for, if we have in our standard linear regression, so we've got a coefficient of 1. What does that coefficient of 1 tell me? What do you think, Emilio?
For every unit increase in x, everything held constant, 1 increase.
Right, and let's, okay, so let's say it's we have a coefficient of 2, what is that, holding everything else constant, my unit increase in X is associated with the 2 unit increase in Y, okay? So what if I do a 2 unit increase in X? What's my expected increase in Y?
You mean if X was?
If X is, so instead of going at a 1 unit increase, let's say a 2 unit, what's my expected outcome increase in Y? So if my coefficient is 2, right? And so that's not, it's going to be 4. There we go. Okay. And what if I say a 3 unit increase? What is it going to be? 6, right? And so we sort of go. So it's kind of an additive function. This is going to be different because if my log odds 4, if my coefficient, if my odds ratio is 2.0 in this model, right? And so I'm saying a 1 unit increase results in a sort of the odds of occurring versus not occurring sort of increase by 2. If I go through and I say, so 1 unit increase is 2, so this is my coefficient, right? This means if I have a 2 unit coefficient, I have, or 2 unit increase, this is going to give me 4. If I get a 3 unit increase, now what's going on is I'm saying 2 to the 3rd power. So it's 2 times 2 times 2 is still 6. Damn it. Should I use 2? How about this? 3.
Don't you need 8?
Oh, yes, thank you. Never mind, 2 works. Emilio wins, I lose. There, 8, okay. So we're getting differences. So this is a multiplicative function in terms of the increase. And this starts to become really important because when we're looking at our continuous predictors, right? A 1 unit change in my predictor may not mean much, right? But if I've got a continuous predictor that has a wide range, as those values start to increase, the odds of occurrence versus non-occurrence start to jump up very, very quickly, okay? And so we're working on a kind of a different scale here. And so again, here I would say that the odds ratio is saying that holding other predictors constant at 0, the odds of falling versus not falling multiplied by 2.75 for every unit increase in slope difficulty. So the odds of falling versus, so for trail difficulty 1 versus 2, so the odds of falling versus not falling on a level 2 difficulty trail are 2.75 times as likely as the odds of falling on a level 1 trail, everything else being held constant at 0, right? Or I would say the odds of falling versus not falling increase by 175%, right? For a trail 1 versus a trail 2, right? So we say 175% increase, right? So the odds of falling versus not falling on a trail 1 versus trail 2, 175 increase. We're talking about 1 versus 3, right? Now what we're doing is we're taking 275, 2.75 times 2.75. What's that?
7.563.
7.563, right? So I'm saying now I've got a 656% increase if I go from a level 1 to a level 3. So I've got a 2 unit increase here. And a 2 unit increase is then, that means I multiply my odds each time if I'm jumping from a 1 unit increase to a 2 unit increase. And then if I were to go 3, it would be 2.75 to the 3rd, right? And so what we've got is an exponential increase in these odds. And so this starts to make a great deal of difference if I'm working with a continuous scale. And it looks like my odds ratio is quite small, right? But if I have a 0 to 100 scale, and we've got a large range of things, right? that can start to mean sort of very, very large increases in our outcome. And so sometimes when you're working with these logistic models and we're working with continuous measures that have a sort of very fine-grained scale, starting to think about things. A 1 unit increase in sort of my 0 on 100 scale might be sort of nothing, right? But starting to think about things in terms of standard deviation unit increase. Standard deviation unit increase associated with this increase in the likelihood of occurrence versus non-occurrence. Okay. So people see how this is what we're working with differently in our logistic models versus our standard linear regression. Okay. So again, going back to our odds ratio, our odds ratios that are greater than 1 are associated with an increased likelihood of our outcome. So if I've got an odds ratio of 1.5, I'm saying the likelihood of an event is 1.5 times that of a non-event, given a unit increase in my predictor. Okay. Alternatively, I could say odds are increased by 50%. Nick, can you tell me how did I go from an odds ratio is the likelihood of event 1.5 times of a non-event given a unit increase? How did I get to say the odds are increased by 50% based on that odds ratio?
That's the difference between
Right. So I take my odds ratio, subtract it from 1, I get 0.5, and just tell me I have a 50% increase, right? A 5-unit increase, however, associated with a 659% increase in my odds. Yeah, how did I get that? What do you think, Kate?
1.5 to the 5th, and then minus.
Yeah. So 1.5 to the 5th is what?
7.59.
7.59, right? And so what we did is, again, remember that it's a exponential function with these, and I multiply my odds for every unit increase here. And so if I'm talking about an odds ratio of 1.5, so saying a 1 unit increase increases the likelihood of event versus a non-event by 1.5 times. If I'm talking about a 5-unit increase, I'm taking 1.5 times 1.5 times 1.5 times 1.5 times 1.5. Now I've got my odds ratio is 7.59. Subtract that from 1, that's a 659% increase in the odds of occurrence versus non-occurrence, with you given a 5-unit increase in my predictor. Okay, so things start to jump up very quickly when we're working with these models. Okay, so this is our odds ratio greater than 1, odds ratio less than 1. This is speaking of the decrease in odds, right? We're saying, let's say we've got an odds ratio of 0.8. We're saying the likelihood likelihood is 0.8 times that of a non-event. The likelihood of an event is 0.8 times that of a non-event, given a unit increase in our predictor, right? Alternatively, I could say the odds are decreased by 20%. Haley, how did I get that?
You just subtracted the odds ratio from 1.
Yep, do 1 minus 0.8, right? And you're left with 0.20. And so if we were more comfortable talking with this, I talk about, and this is probably an easier way to talk about this, that odds ratios less than 1 are a little bit tricky, because it's talking about a decrease in odds. But if I'm saying that the likelihood is 0.8 times that of a non-event, what I'm saying is it's decreased, but that's not maybe clear unless you're sort of familiar with this type of thing. What I can do is take that, subtract it from 1, and just say odds are decreased by 20%, given a unit increase or decrease in the predictor, something along those lines. Okay, and then once again, I can say a 5-unit increase results in a 67.2% decrease in the odds. Right there, I just took 0.8 to the 5th power, and sort of went through and then said, so this is the percent reduction in odds for this versus that. Okay, this can be tricky to go through and interpret. Go through and take a look at that handout with that email. Sort of going through, talk about different ways of talking about and interpreting things. This will be helpful in terms of as you go through and work through your interpretations with some of these models. Okay. We'll kind of get a general sense of what's going on with these. So effect sizes with our logistic models, there are a number of pseudo R-squared statistics sort of this overall model fits, these cannot be interpreted the same way we would interpret our R-squared for our linear regressions. The relative benefit of these is highly debated. Probably you don't have to worry about pseudo R-squared statistics. There's about 1,000 of them. This is what they are. There are different weird ways of sort of going about trying to calculate sort of the overall fit in a standardized way, but they're generally not reported, so you don't probably have to worry about this. But for your individual predictors, odds ratios in and of themselves can be used as helpful effect sizes, right? If we're talking about, if I say the odds of occurrence versus non-occurrence giving you an increase in this thing or that, or the odds of occurrence for this group versus that group is 10 times that of the other group, that means a lot, right? So our odds ratios in and of themselves can be used as a metric of effect. We can also convert our odds ratios into an approximate D if we just want to get things kind of standardized on small, medium, and large. Downside of this is, I mean, it puts on a metric that sort of is people sort of are associated with benchmarks. It doesn't mean anything in terms of D's as we typically calculate them or interpret them. It just kind of converts it to a different metric that doesn't fit, but can be useful in terms of just gauging magnitude of effect, right? We can also convert D into an eta squared. That again puts it onto a metric, but again isn't a metric that actually interprets. You're not interpreting anything as proportion of variability accounted for. You're not talking about this in terms of units of standard deviation change across group 1 and group 2. So these are conversions that you can do in terms of rough approximations. What you shouldn't do is apply our usual interpretation of D or eta squared for this. It's just to put it on a comparable metric, right? Sort of like if we were sort of in a meta-analysis and wanted to convert everything to R's. I mean, just for the purposes of comparison, you could do that, but just be careful with some of this stuff. All right, assumptions of our logistic models. One, adequate specification. We want to make sure that things that are in there need to be in there, things that don't need to be in there aren't in there. Our model tends to be more powerful when our variables are multivariate normal, so we're still going to go through and screen, just kind of eyeball things and see what things are going on. But our data don't need to be multivariate normal in order to, it doesn't violate an assumption if we do have problems with normality of our predictors and our outcome. More importantly, we need to make sure that our outcome is not perfectly determined by any variable or set of variables. Okay. Sometimes when we have small samples, particularly if you have large designs with a number of different categorical variables, everybody in this group meets criterion, everybody in the other group doesn't meet criterion, and if you got a cell in there where it perfectly predicts outcome just by chance, just because of random stuff, that'll crash your model. So you need to be careful. Generally more concerning with small samples. What you'll see is failure for that model to converge. You'll get an error. You'll get large parameter estimates with massive standard errors or things like that. Basically, this is the equivalent of dividing something by 0. So just being careful there. Also, similar to, think about like our basic chi-square models, right? We want to make sure that we have adequate representation in all of our cells. If we have cells that have 0 counts in them, that starts to become problematic. For our logistic models, we want to make sure that our expected frequencies in all of our cells are greater than 1, with less than 20% of our cells having expected frequencies less than 5. Okay, and so we can go through and take a look at contingencies tables, make sure that we're good there. This gets a little bit tricky. What we need to have is a linear relation between our contingent predictors and our logit. Okay, so our logit is our log odds, and our variables themselves don't have to hold linear relations with anything. But what we need to have is that our logit, or our log odds of our outcome, holds linear relations with our logit. What we're going to do is we're going to screen this quickly. We're going to calculate interactions between our continuous predictors and their natural log transform. And as long as we don't see an interaction between the predictor and the the predictor and the natural log predictor, we're going to check this off and say, yep, we're good to go there. Okay. Want to have absence of outliers or problems with multicollinearity, and then we need to make sure that our observations are independent of one another. You know, Laura's score isn't sort of influenced by John's score, isn't influenced by Nick's score, things along these lines. Okay, so we're still going to go through and we're still going to screen, right? Because it's always good to just have a general sense of what your data are doing. It'll give you more familiarity with what's happening with your model. But what's nice is that we can violate, so we can have weird distributions. We're not going to be too worried about that. You know, we don't have to worry about homogeneity of variance and heteroscedasticity and some of these types of things. So it's a much more manageable set of screenings. And if we do start to see weird stuff, it doesn't necessarily impact the quality of our results. Okay. All right, we don't have to worry about that. This is different stuff. Okay, ready to walk through one of these models? Cool. All right. So, you open up your data file here. This is Arena data. Arena generally did data. And grab your, it's the binary logistic exercise, binary logistic stuff. Okay, that handout. Okay, so what we've got is we're trying to predict whether or not individual jurors voted to assign life in prison or death sentence to based on sort of this hypothetical case, right? Not a hypothetical case, not a hypothetical case, hypothetical cases. So sentences are outcome. 0 is life, 1 is death, right? And so what we're interested in here is the probability of death sentence versus not death sentence. So we've coded this intentionally. So 0 is our comparison group, 1 is our criterion, which in this case is juror voting for the death penalty. Okay. We have a number of victim impact statements introduced by the prosecution. Nick or Haley, you want to tell us about victim impact statements? What's going on with those?
It's essentially in a case where someone's been hurt or killed, the family can read a victim impact statement, which kind of influences, or I wouldn't say it tries to influence the jurors, but it just kind of tells how they've been impacted by the crime.
So what we're looking at here, for each juror, the number of victim impact statements that were delivered within the case. We've got a measure of depravity. You guys, any idea on how they measure the depravity of a case? Okay. We've quantified it, I guess, from 0 to 100 scale. 0 being not at all depraved, 100 being horribly, like someone ate somebody or something like that.
Maybe it's more like gruesomeness. I don't know.
Could be, right? So some sort of 0 to 100 rating of the depravity, the subjective depravity of the homicide. And then we've got, so we're going to treat a number of victim impact statements and depravity, both of these as continuous indicators. And then we've got VIS delivery. This is our categorical predictor. And so we're saying that 0 means that no victim impact statement was delivered, which ends up being collinear with another one. We're going to ignore that for right now. 1 means that it was in private, 1 with a question and answer, and 3 means open, which I don't know what that means. I don't know. But so basically we've got a categorical variable with 4 levels to these data. Okay, and so what we want to know is, does the best linear combination of number of victim impact statements, depravity score, and the delivery of victim impact statements, do these best linear combination of these variables, does that predict whether or not jurors vote life in prison or death sentence? Okay. Questions about how we're going to go through what we've done here? All right. So first thing we want to do, again, even though we are have much more manageable in terms of our assumptions of our variables, we know that if our data are multivariate normal, it just kind of helps out in terms of things. And so what we're going to do is we're going to go through, run our descriptives, and we're going to look at a number of victim impact statements, our depravity score. We're going to request skew and kurtosis values. And I'm going to go through and paste that. If I run that, Laura, what am I seeing in terms of my skew and my kurtosis values for these two things that I want to treat as a continuous variable?
Not looking good.
Not looking great. Not looking too good. Why do you say they're not looking great?
They're pretty high, especially the kurtosis ones.
Yeah, we're super high skew, super high kurtosis, right? If we were planning on running a linear regression model, this would be bad news bears, right? If we go through and we want to go back to analyze, descriptives, explore, we're looking at victim impact statement, depravity score, plots. Take a look at these variables. Yowza, right? That's not so great. We've got some way out there in terms of victim impact statements. And we've got depravity scores. We've got a couple of mostly not so depraved, but then we've got some gruesome bad stuff going on here, right? And so we've got clear problems with the distribution of these in terms of if we had assumptions about linearity, okay? But the nice thing about our logistic models is we're not necessarily, we have no assumptions about the distribution of our continuous predictors, right? So we're gonna, so even though, and this would be something to note and to think about, like, does this make sense given sort of what I understand about the measurement of these constructs? It doesn't necessarily screw with our with the assumptions of our model, right? Which is nice when you're dealing with stuff like this. Okay. Now we're not going to go through and run formal tests of outliers and things like that. You would want to go through, calculate your z-scores, things. Now, even though we don't have assumptions about the distribution of our scores, we've got someone who's way out here in terms of the number of victim impact statements. It looks like if we go back through and take a look at go through and just sort this. Looks like we've got one person with 14. I would probably want to go through and check that to make sure that wasn't a 4 or something along those lines. If it is, if this is a case where someone gave 14 and the next one is 6, what might I want to do with that case? What do you think, Kate?
So you can smooth it?
I'd probably smooth it, right? I'm not going to transform the variable because that doesn't make sense because I don't have assumptions about the distribution of the variable. But I do have we do still have concerns with outliers, right? And this, we've got 123 cases. It's probably not going to be, it's a reasonably large sample, but this is a clear outlier, right? So I would probably maybe just smooth that and set that at 7, probably, if I were going to go through and run these data on my own, right? If I'm going through and taking a look at depravity score or depravity, again, it looks like I got one case. My max here for depravity is 73, which in terms of a univariate outlier is, I don't know. Mike, what are my options here? What might I do with this case? My thought process be for, do I need to do something with this case? Do I not need to do something with this case? What are we thinking? Go for it, Kate. What are you thinking? Yeah, and that's kind of what I'm worried about. Like a case with 14 victim impact statement, that seems weird, and it seems not representative of the rest of my sample. So I'm okay probably smoothing that. Here you could say, well, it's outside, so it's high. The whole distribution is kind of skewed. And this maybe represents a unique case on the end where you've actually got a case that was like bad. I could smooth it, but then that sort of reduces the fact that sort of this is maybe one case. I don't know. I don't work in this area. I would imagine the number of cases where you have people doing weird stuff is probably not super common. And so I don't know that I want to screw with that if I actually did get a case in here that captured it, right? We've got a score, a set that's big, right? It's a 0 to 100, so it probably falls within the range of sort of what we would expect. So in terms of, I might run this with and without sort of that thing. If it's the one case that tries the whole model, then I'd maybe be a little bit concerned about it. But if the cases are robust, or the effects are pretty robust, if I smooth that versus I just kind of leave it the way it is, I'm going to leave it the way it is too. So I sort of wanted to walk through and think about it. And so this is where we start getting in trouble if we start thinking about things in terms of hard and fast rules about, like, oh, if it's above this, you always have to do this. I mean, example 123 isn't huge, but it's decent-ish. Probably this case isn't so far out from some of the others. The difference between me smoothing that and it staying where it's at probably isn't going to be a huge impact on things, so I'd probably play around with that. I would maybe be reluctant to jump in and screw with stuff, particularly if this is a unique case that you're hoping to get. You already, like, I would assume you want to get these cases to try and test the end of the thing, and then you undermine yourself by then sort of making it look more like the cases that you've already got. So want to be careful with this. So for these, we're not going to, in this example, we're not going to go through and mess around with anything. We'll just kind of leave it where it's at. But these are some of the thought processes you might want to go through and think about. So looks like our continuous indicators are problematic in terms of their distribution if we were to be running a linear model or a linear regression, but we're not. We're running a logistic model, and so we're going to be okay. We're more tolerant about some of this stuff. Okay. So other thing I'm going to do now is I start to become concerned because I do have a categorical variable, right? And what I might be concerned about is making sure I have adequate representation across my cells. So what I'm going to do is I'm going to go to Analyze, Descriptives, and then I'm going to go to Crosstabs. And I'm going to put VIS delivery as my rows and sentencing as my column. And then I'm going to go to cells, and I'm going to want to have expected values in my cells. Gonna think that, continue that, that should be good. And I'm going to go through and paste that. That should give me, yeah. And then we can go through and take a look at this. All right. So, Laura, what am I looking for in terms of this table right here?
The ratio difference between different cells.
Okay. And so I could eyeball that and kind of look at ratio difference. And it looks like I don't have even distributions, right? But that's fine. I don't need that. Remember what I'm looking for here for these models, I want to make sure that my expected values for each one of these cells is at least greater than 1. Okay? So is my expected count greater than 1 for all of the cross tabulation of sentence and VIS delivery? Looks pretty good, right? So I don't have any, there's no cell that I have in this where the expected value is less than 1. And do I have less than 20% of my cells with the expected value, or at least 80%, or is there no more than 20% of my cells with expected values less than 5? think, Nick?
You're good.
Yeah, I'm good, right? My expected values for all of these are greater than 5, so I'm good here. So again, what I want to do, I want to make sure that in this analysis, I'm not dealing with sparsely populated cells, because then that starts to become problematic. If I don't have adequate representation in some of these, and this can start to become problematic as we start to get categorical variables with a large number of levels to them, or if we have samples that are quite small pretty soon, or if we're looking at, let's say, outcomes that are very unlikely, right? Here, looks like we've got a reasonable distribution of death versus not right here. And so our outcome, but if we're looking at something that's an outcome, so some sort of rare outcome, the prediction of schizophrenia or bipolar or school shootings or like sort of violent crime or something like that, where I've got, 15 people in one cell and a bunch of people in another cell, and then I have a bunch of different categorical variables, then that starts to become problematic, right? But here it looks like we're okay. So what I'm going to do, so it looks like we've got crazy distributions, but that's fine. Our adequate representation in our cells. And so what I'm going to do now is going to, oops. We want to go through and center our variables for our eventual logistic model, but then I also want to make sure I want to test the linearity of my logit. So I'm going to compute, we call it C impact is equal to my number of my victim impact statements minus, go through and take a look at my descriptors, give me my victim impact statement is going to be 1.4878. And go compute. Call this one C. Gravity is going to equal to gravity minus, gravity score of 12.5041. Okay. So now we've got my centered variables. Okay. But now what I also want to do, because to test the linearity of my logit, what I'm going to do is I'm going to create interaction terms between my continuous predictors and the natural log of the continuous predictors. And what I want to do is I want to make sure that I don't have interactions between those two things, which suggest nonlinearities. And so what I'm going to do now is going to create a couple more variables. I'm going to go to compute. Natural log impact is going to be natural log 1 plus VIS and we'll do the same thing. Compute. Call this natural log dependency, or depravity is the natural log of 1 plus my depravity variable. Okay. So what I've done is I've gone through and I've created my centered variables. We always do this, right? What I've now done is I've calculated the log transform of my number of impact statements my depravity ratings, and I've created log transforms of these because what I'm going to do is I'm going to run a model where I'm looking at the interaction of the continuous variables and their log transform. And if that interaction turns up as statistically significant, it suggests that there's some nonlinearity in my logit, which starts to become problematic, and I have to go through and figure out how to account for that. Okay. So what I'm going to do, I've already gone through, calculated my my centered variables. I'm going to calculate my log transforms. Here's the log transform of impact, log transform of my depravity scores. And so now I've got everything that I need for my model. Okay. So I'm going to go to analyze. I'm going to go to regression. I'm going to go to binary logistic. My dependent variable is sentence. Okay. My covariate is going to be, centered depravity scores. Okay. And then I'm going to also go through, and I'm going to go and I'm going to select centered impact. And if I hit shift, I hit the nav. There we go. If I click on impact and then I hold down control and hit the natural log of impact, this little button down here that says A times B, I can click that and it just creates the interaction term for me in the logistic model. So this is nice. I don't have to create an interaction term sort of in terms of a variable. And then I can hit my center depravity, hold down control, select that natural log of my depravity score, and drop that in there. Right, so that gives me that interaction, which is nice. And then what I can do, then my VIS delivery, this is going to be my categorical variable. So I'm going to drop that down in there. Okay. So I've got impact, centered depravity. The interaction of centered impact and the natural log of impact, the interaction of natural log of dependency and depravity and the centered depravity, and then my VIS delivery. Okay. VIS delivery is my categorical variable. So what I'm going to do is I'm going to go up here to categorical, and I'm going to click that, and I'm going to tell, hey, SPSS, VIS delivery is a categorical variable, so treat it as such, right? So what's nice about this is the way SPSS has this set up, you can go through and tell it which variables are categorical, which variables you want interaction terms. This saves you a lot of space for having to go through and calculate things on your own like we had to do for your standard regression models. Okay. Now here, you can select different types of, you can tell SPSS how you want it to model that categorical variable. We're just going to leave it on indicator. Okay. And then, other thing that you want to make sure that you're doing is you're wanting to go through and you need to make sure that you're identifying which one of these is the reference category. Okay. So VIS delivery is coded 0 none, 1 private, 2 question and answer, and 3 open. Right. Right now, the default for SPSS is to use the last category as your comparison group. This doesn't seem to make sense for what we're doing here. I probably want the first category to be my reference group, right? So what I'm going to go through is I'm going to tell it, hey, I want the first category to be the reference group. That way, what I'm going to get. So John, how many dummies am I going to get for VIS delivery?
3.
3. And what's going to be the reference group? None. Okay. And so what I'm going to go through is once I've told it to switch that to the first one, and I'm going to hit change. If you don't do this, it won't save it. So make sure that you go hit through and hit change. And so I can go through, I can see VIS delivery. I'm creating indicator variables for this with the first group as my reference group. So I'm happy with this. Okay. Go ahead and continue. And you can see I've got my 2 continuous variables, the interactions that I'm going to use to test the linearity of my logit, my categorical variable. Then I'm going to go through, if you check or take a look at this. Here you can save predicted probabilities for each case, group membership, all sorts of different stuff going on, different things that you can save in terms of your output that can be helpful when you're running these models. We're not going to do anything with this right now, but you can look at influence statistic leverage values, different things to go through and do screening here. You can predict, save a, well, I'm just going to do this. Probabilities and group membership, I'm just going to click those two. What it's going to do is it's just going to create new variables that, based on my model, tells me the probability of death versus no death, and it's going to tell me whether or not, based on the model, I'm predicting whether or not people, for individual cases, whether or not the model predicts that that person would sentence group, death or life. So we'll just do that just to show you how that's going. And then in terms of options, what we're going to do is you can ask case-wise residuals. It's going to tell you if you got weird stuff going on there. We're going to go select confidence intervals for my exponentiated for my odds ratios. We're going to continue here, and then we can go through and paste this in. Okay. So we've got my model, and we've done a lot of stuff here, but we'll just get it out of the way on the front end. Go through and run my model. Actually, I probably shouldn't have done that. So this isn't actually the model that we're going to run. So predicting probabilities and groups, I guess, wasn't necessary for this one, but you saw what it did there. What we're really going to do here is take a look at our outcome. You can scroll through a lot of this. Don't have to worry about it right now. But if we're looking at our outcome, remember that the whole reason we ran this model was to test the linearity of our logit. Do we have concerns about linearity of our logit for this model? What do you think, Evelina?
Yeah, for VIS delivery.
Okay. Well, so what we're looking at, remember, linearity of our logit, we need our continuous variables to have not to evidence a nonlinear relation with my outcome.
So no.
Right? So no. And so what coefficients are we looking at for in terms of statistical significance to test this?
Significance coefficient?
Yeah. Which for which coefficients? Or for which predictors?
For the wall.
What's that?
Wait, what?
For the wall. So in this, there's a lot of different predictors in here. Which ones, for this purpose, which ones are we most interested in?
The two interaction terms.
The two interactions, yeah. So we see here in my two interactions between the natural log of impact and the centered impact, and the natural log of depravity versus centered depravity. Those aren't statistically significant. We don't have evidence of nonlinearity in our logit, so we're feeling pretty good about this. Questions about what we've done to this one? Okay. So for the purposes of this assignment, we'll say good enough with this, and we can go through and we'll proceed to our actual model. But what's nice here is we've already sort of got our model, right? So I can go through and just cut this and then paste this down. And then all I need to do, I just need to pull out my two interaction terms. Because that was just for screening purposes, and now we just have our model, right? So we're looking at regressing sentence or dichotomous outcome onto centered impact, number of impact statements, centered depravity score, our VIS delivery. We've identified VIS delivery as a categorical variable, where we've got an indicator, where we're looking at the first group as our reference group. We're going to save predicted probabilities and group membership based on the model. Going to ask for some outlier stuff. We're going to print 95% confidence intervals, so on and so forth. So we're going to go through and run this. Okay. How are we feeling up to this one? Okay? All right. What we want to do, and again, with any of these models, when you're running any type of analysis, always want to go through and make sure that what the model is telling you fits with what you think you told the model to do, okay? So our first table right here is telling us how many people we had included in the analyses, how many missing cases, 123. Okay, cool. We didn't miss anybody. We got the total number of people in the model that we think should be in the model, so we're happy about this, okay? If we look at dependent variable encoding, life is coded as 0, death is coded as 1. This means that we're looking at the odds of death versus the odds of life. Incredibly important. I can't stress this enough when you're working with these logistic models, that you need to make sure that you double check who your reference group is, because otherwise you're going to be all backwards on your interpretations. Okay, so here we wanted death sentence to be our criterion, life is our reference group. We've coded this correctly here, so we're excited about that. Down here, categorical variable codings. This is important because this is going to tell me, make sure that for whatever categorical predictors I have in there, are coded the way that I think they're supposed to be coded, right? So for my none group, 1, 2, and 3, 0, 0, 0, this is telling me I've got 49 people in the none. This is my reference group, right? My parameter coding 1 is set as 1 for private, 0 for 1. For parameter coding, my first indicator, or my first dummy is going to be 1 for private, 0 for everything else. My second dummy, 1 for question and answer, 0 for everything else. My third, 1 for open, 0 for everything else. Looks like that none is my reference group here. I've got 3 dummies. This is all looking to be consistent with what I had wanted to do. And again, please, please, please check this and don't ignore this, because it'll make sure that you don't sort of make errors as you're moving forward with stuff, okay? All right, people comfortable at this point? All right, so what SPSS will do is it'll first give you your beginning block, okay? Beginning block is giving you stuff in the model where there are no predictors. This is a model with no predictors, okay? And your classification table tells you, for a model with no predictors, how is it identifying people in terms of whether or not they're experiencing life or death, or excuse me, whether they got sentenced to life or death. And Haley, what's going on in my prediction table here?
Is it, since you're holding everything else constant, it's predicting death only, because that's your group that you're comparing to?
Okay, close. So again, for this beginning block, how many predictors do I have in this?
None.
None, right? So basically, if I'm looking at what actually is observed, right? So I have 52 people that were sentenced to life, 71 people who were sentenced to death. In the absence of predictors, what's my best guess on whether any one individual case is sentenced to life or death?
They're going to be sentenced to death.
Yeah, you just pick the most common category. In the absence of any predictors, just like in the absence of any predictors, my best guess is me. In the absence of any predictors for a logistic model, my best guess is the most frequent observed category, right? So in the model, in the preliminary model, without any predictors, my best guess is just assume that everybody got the death sentence, and it looks like I'm right 57% of the time, okay? But that's just because 50% of the cases were got death sentences versus life, and so that's what's going on in the model here, okay? Variables in my equation down here, this is just giving me, all I've got is a constant because I have no predictors, right? And what this is giving me in this odds, or my coefficient here, in my exponentiate, so here's my coefficient. So this represents the change in log odds given a unit, well, this just gives me the log odds for the full model, right? Basically, in the absence of predictors, if I exponentiate this out, this is giving me the odds of death versus the odds of a life sentence, right? And it's about 1.4, okay? So I would say that based on, in the absence of any predictors, just on sort of the base thing that I'm looking at this in these data, I would say the participants in this are sort of participants in this study, 40% more likely to provide a death sentence versus life in prison. Okay. In the absence of any, that's just kind of the state of affairs, right? Because we're saying, looking at the odds of death sentence versus the odds of life sentence. Now, if we take a look at my statistical significance, it looks like that's not reliably different than 0, so we're basically saying that that's not reliably different than even odds here, but wanting you to understand sort of what this classification table is doing and what this sort of base equation is doing right here. People kind of seeing how this maps onto some stuff that we've talked about. Okay. If we scroll down, you'll see this last table of variables not in the equation. This is your score test. These are your Lagrange multipliers. You don't have to worry about those. It's just basically a different way to calculate change in log likelihood, which isn't as good as just manually calculating the change in log likelihood. So you don't need to worry about this at all. Okay. So that gets us through our beginning blockage. So our beginning block is just going to be the model with no predictors in it. Okay. But then if we go down through and we take a look at our block 1, this is telling us, okay, this is a test of our model, okay? And so, our first omnibus test of model coefficients, what this is telling us is this is our test of our overall model, okay? And Emilio, what's our test of our overall model here? What is it saying? Is it statistically significant? Yes, and we're just looking at step 1 block model, they're all the same thing, right? And so this is just telling, this is like our ANOVA table, analogous to our ANOVA table with our regular regression models. This is just saying, does the best linear combination of depravity score, victim impact statements, and VIS delivery, does the best linear combination of these variables do a better job of predicting outcome above and beyond no predictors at all, right? And this is saying that, yep, the inclusion of this set of predictors does a better job of predicting this as compared to nothing at all, right? What this is this is giving you the change in log likelihood from your full model relative to the model with no predictors. Okay. So what this is saying is, if you take down, look at here, your model summary, this is giving you the -2 log likelihood for your model, right? So -2 log likelihood for my model is 146.519, okay? What this is testing is whether or not your log likelihood for your model with all your predictors is reliably smaller, reliably different than the log likelihood of your base model with no predictors in it, okay? This is basically your chi-square change, this is giving you your chi-square change statistic. So this is represents the difference between the log likelihood of your full model versus the model without predictors, tested against 5 degrees of freedom, okay? Can someone tell me where those 5 degrees of freedom came from? What's that? Yeah, you're right, right? So basically, if we go down through and take a look at the variables in my equation, I've got depravity score, I've got centered impact, and then I've got 3 VIS dummies, 1, 2, 3. I've got 5 predictors in my model, right? So what this is saying is that my model with 5 predictors is reliably, the fit of this model with 5 predictors is statistically better than the model with no predictors in it. Your model chi-square, or your chi-square test here is going to be the difference between your log likelihood for your model that you've got here and the log likelihood value for your model with the block 0 model with no predictors. Okay. So basically, we were just taking a look at the difference in those log likelihood values. Okay. And if we go down through and we take a look, so we know that the best linear combination of these predictors does a better job in predicting my outcome, life sentence versus death, as compared to just nothing at all. So that's good. Here, if I take a look at my classification table, has this classification table changed relative to the base model? What do you think, Layla? Yeah, why did it do that? Now we have predictors, right? We don't just predict sort of the most frequent category of our outcome. We can actually use this model to start to predict kind of where people are at, right? So it looks like here we've got, if death is our criterion and life is our reference group, so we've got, we observed this was life sentence versus predicted life sentence. This is our true negatives here. Here's our true positives. So we observed someone give the death sentence, and that person actually was predicted to give the death sentence. We've got this. Here, we've got people who were observed to give a life sentence. We predicted in terms of our predictive model, this is a false negative. We said that it was not going to be criterion, but it actually was criterion. We've got a false negative here. Here in the upper corner, we've got false positives, right? This person gave life in prison. The model predicted death, so we've got a false positive there. So we could work through, calculate sensitivity, specificity, positive predictive values, negative predictive values for all of this, so start calculating, sort of giving a sense for, we know that this model is statistically significant, so this the combination of predictors does a better job than just guessing the most frequent category, but we can go down through and use this to now go through and look at the practical utility of this model. Okay, and so what we're seeing here is an incremental increase in the number of correctly classified cases. Before it was what, 57 or something like that, just because 57% of the sample. Yeah, 57.7. We've gone from 57.7 to 64.2. We've got some incremental increase in the classification of our outcome. Questions with this? All right. Going down and taking a look at our the variables in our model. Looks like we have a statistically significant effect of our depravity score. It looks like VIS delivery as a whole, right? This categorical variable as a whole is a significant predictor. But within these individual dummies, it looks like VIS delivery 1 is the only one that's associated with a unique effect within this, right? So this is for the overall group of predictors. This is looking at individual contrasts here, okay? So if I'm looking at my centered depravity score here, my coefficient, right? The expected change in my log odds given a unit increase in my depravity score is 0.101, right? And if I go through, we see with my Wald test, that's statistically significant. If I exponentiate this out, my odds for every unit increase in depravity score for the odds of death versus life is going to be 1 point, let's say 1.1. All right. So what I would say is I could say that a 1 point increase in depravity increases the odds of death versus life by a factor of 1.1. Okay. Or I could say a 1 point increase in depravity score associated with an 11% increase in the odds of death versus life. Okay, I've just taken this and I've subtracted 1 from that. 11% increase doesn't seem to be a whole lot, right? But if I would say a 2 point increase is associated with a 23% increase of odds of death versus life. Okay. If I were to go through a standard deviation increase, if I go back through and take a look at the standard deviation of my depravity score, right, is going to be about 9. Right? Yeah. Okay. If I do that, if I say a standard deviation unit increase, right? So I would say then one standard deviation unit increase in depravity score associated with a 148% increase of the odds of death sentence versus life in prison. Okay? And that's if I take my odds ratio of 1.106, if I have standard deviation of about 9, right? That's going to give me what's 1.106 to the 9th power. Based on my notes, it looks like the standard deviation of depravity score was about 9, and so this just represents the unit change. So what do you get for that, Laura?
2.476.
So 2.476, right? So we go through and sort of round this, sort of subtract 1. So we get 148% increase in the likelihood of, or in the odds of death versus the odds of life, given a standard deviation increase in this, right? So even though this is a very small, remember our depravity scale goes from 0 to 100, so a small unit increase, sort of that starts to add up within our model. Okay. So this is ways we might interpret our depravity score. Overall, it looks like VIS delivery does have an impact. That does, having that variable in there does improve prediction. But if I go through and I take a look at my my first dummy, what is John? What is my first dummy code for VIS delivery? What's the comparison that I'm looking at there?
You'd be comparing your private delivery versus none.
Private versus none, right? And what it looks like based on this model is it looks like, and again, we've got a negative coefficient here, and if we exponentiate this, we've got our odds ratio here of 0.261. So what is this telling us? What happens to the odds of death versus life when I'm comparing a private VIS victim impact statement versus not at all? What does that do to the odds of life versus death? Decreases it, right? So based on this, I could say that the odds of death are 0.26 times as likely as the odds of life when a VIS is presented in private versus not at all. Okay, and this starts to get tricky because you have to keep track of what group we're talking about versus what, right? So I could also say that the odds of death versus life decrease by 74% when VIS is delivered in private versus no VIS statement at all, right? And so we can start to go through, depending on whether or not our variables are categorical, and starting to sort of move back and forth and talk about these in ways that are helpful. People kind of see what's going on in this outcome and where things are at and how things are looking. It looks like our nothing came up in terms of case-wise diagnostics and stuff that's weird or terrible. So I guess it didn't do too much that we had someone who was kind of an outlier. We didn't do anything, so nothing came up here. So feeling pretty good about that. Questions? All right. One last thing we want to do, just to show you in terms of application of how to calculate differences in negative log likelihoods. So on the last page of your handout, you see we got 2 scores. And what maybe I want to do is I want to take a look at, so VIS delivery, depravity score came up as a statistically significant effect, right? But maybe I don't trust my walled statistics. I want to actually look at the change in -2 log likelihood across what that variable included or not included. This is pretty easy to do. what I can do is I can take my model here and go down through so I get some space here. And what I'm going to do is I'm going to compare a model that has impact and delivery, but it doesn't include depravity score. Okay? So I'm going to run a model that just is looking at impact, centered impact, and BIS delivery as predictors. And I'm going to compare that against a model with all three of my predictors in there. Okay. So I'm going to go through and I'm going to run these together in my output. So here I have my log likelihood for my model. This is my full. This is my reduced model, right? My reduced model. My log likelihood value for my reduced model is 156.713. Okay. And then what I can do is I can go down through and I can take a look. What should this log likelihood value do if the inclusion of depravity score improves the model? What should happen to my log likelihood value? It should decrease. It should get better, right? And so if I go down through and I take a look at the log likelihood for my full model, this is my model that has all of my variables in it. So the log likelihood value for my full is going to equal 146.519. Okay. So if I go through and I say this is the fit of my model with just my two predictors, and this is my categorical predictor and my number of impact statements. This is my log likelihood for my full model that includes depravity. What I can do is I can go through and subtract these. And this is going to give me a log likelihood difference of 10.194. Okay. And so what can we do with that, log likelihood difference? What's that now?
Would you compare that to the wall?
We can compare it to a walled, right? I mean, the metric's not the same, but what is this log likelihood difference value? How is it distributed?
The same as a chi-square.
It's chi-square, right? And how many? What's the difference in the number of predictors we had in my reduced versus my full model? Just the one, right? So I can say, so a chi-square with 1 degree of freedom at alpha equals 0.05, my critical value is 3.84, okay? So what I can do is I can compare this against a chi-square degree with 1 degree of freedom, and this gives me a more exact test of the unique contribution of my depravity score as opposed to my walled. And if I look at this, this is obviously p less than 0.001. This is sort of not even in the vicinity of anything that would be close to not statistically significant. If we go down through, we take look back through and take a look at your walled statistic. Your walled statistic for depravity. I mean, you can't. They're not directly comparable. But this significance value here is your p-value 0.009, right? So you see that, again, demonstrating that your walled test is not a precise test. It's easy. Our models go through and put that out. I don't need to do this because this is clearly something that's a unique predictor within the context of this overall model. But, you know, I might go through and, well, it's hard to do this for your individual. We'd have to restructure the model a little bit to go through and take a look at that one. But just looking at with the log likelihood values, think about this in terms of your R squared. You can start to use difference in your log likelihood and your -2 log likelihood values to start going through and getting precise tests of the unique effect of individual predictors or combination predictors if you don't want to go through and use your walled stuff. Now, when you're looking at papers, most people just report walled statistics, and so from a methodological standpoint, you can make an argument for if something's marginal with my walled, and then I can eke it across the finish line with my -2 log likelihood. I mean, is that an effect that's going to replicate? And so you start to worry about maybe playing games a little bit with stuff. But if it's important for us to get a precise estimate of the unique contribution of individual predictors, going through and doing this is a better, more methodologically defensible way than just going through and looking at the walls. All right. Questions about any of this? All right, yes.
So for the classification tables for these models, even though we can see that there's unique contribution of depravity scores to the model, when we took it out, the percentage of prediction was better.
Oh, was it?
In the model, yeah. So what does that mean?
So it was 66 without depravity in there, and 64. I was actually start to get at the difference between a statistical improvement and a practical sort of impact on things, right? Probably what that is probably just fuzz in terms of stuff, right? And again, remember that this is log likelihood is just a non-specific sort of metric of how well your model fits statistically, and so that I would probably attribute that to just kind of random error. But just like with a standard regression, we can get a model that's statistically significant. What that means practically is kind of a different situation, right? So just wanting to keep those two things separate. That's a good catch, Haley. Other questions? All right, guys. Oh, what? Yeah.
It's just for screen run, or just like it's on the
No. I mean, just at this stage of the game. I mean, if you could go through and take a look at request leverage values and go through and check things. I mean, really, what I want to do, check outliers, make sure you have a linearity in your load. Describe what your predictors look like. Take a look at your crosstabs to see if you've got weird sort of underrepresented cells, but you don't need to go through and do a ton of stuff like that. Any other questions? All right. Nice work, folks. Thank you for bearing with me. This was kind of a